Hi guys, I'm Hit Ratio. Welcome to my 4th episode of Fun with Electronics. In the previous video, I introduced you to electronics and components. In this video, we're going to start designing the schematic of the robot. But before we start the schematic, we have to understand the data sheet.
Okay, here goes.
Thank God there's a method to this madness. Let me show you. Almost every component has a manufacturer provided datasheet. This SAMD51N19A will be the processor we will use because it has more pins. Every datasheet starts with an overview of the component and its features. It then explains all the functions in detail. Datasheets can be very large. This one is over 2000 pages, but don't worry, you don't have to read everything. You will also find a section that allows you to order variants of a component. This is a high-level block diagram of SAMD51 processor. It explains how things are internally connected. This section shows that the SAMD51 is available with different number of pins. We are going to use this 100-pin TQFP version. The signal description section gives you an overview of different types of connections and the meaning of signal name. The multiplex signal section is by far the most important in a processor datasheet. You can make each pin do different functions. Another important part is to understand where to connect the crystals to the processor to provide the heartbeat. The power section here is showing that this processor can be powered from 1.7 to 3.6 volts. We will be using 3.3 volts, which is very common. The product memory map shows where things are located in the memory. Remember to program this processor. All we have to do is set and clear bits of these areas in memory. We rarely directly program these memory sections. Instead, we use Arduino or Admiral Studio to program the functions at high level. The DRV8825 is a motor driver we are going to use. Of course, the datasheet is much simpler for this processor. This section shows the pins of the 8825 and what we are supposed to do with each pin. Electrical characteristics like this are good to know, but you don't really need to go into so much detail in a typical PCB design. This again is a functional block diagram of the internals of the 8825. This typical circuit diagram is important. This is what will help us understand how to connect each pin in detail. So let's also take a quick look at our Wi-Fi chip we will be using. Again, the overview followed by a detailed explanation of the Wi-Fi module. Types of modules. A block diagram of the connections to our main processor. The pin layout and description. Very important for our schematic. It explains nicely what to do with each pin. The module footprints and layout recommendations. Also very important later in our future layout videos. So I'm going to create a new project in Altium Designer. I'm going to name my robot Caramel because caramel is just yummy. I'm going to leave the default settings. I am going to add a new schematic to my project. We'll save this as Caramel again. Then I'm going to add a schematic library to the project. I like drawing all my components and connecting them to a supplier like DigiKey from the beginning. This allows me to get a ready-made bill of material at the end of the schematic. We will save this as caramel again. So I am going to start with the SAMD51. I will open DigiKey and search for the SAMD51N19A. Since we need to control 6 stepper motors with about 10 pins of control each, we need a processor with at least 100 pins. Also, the M4 and 120 MHz speed will be valuable to us when we program the robot. I'll select this part number and copy it. Go to Altium and supplier search and paste it there. Altium finds the same component from DigiKey and imports all the data about the component. I will import this component into my schematic library. Next, I will hide the name here. Let's open the SAMD51 datasheet with the pin details page. We are using this 100 pin package. I will start placing pins, like in the datasheet. I'm going to match the pin number and the designator pin exactly. Altium will try and increment the pin number and designator name automatically, but we have to edit the name if the name changes. Just to save time, I will speed up the video for things I am repeating. I guess you get the idea of what I am doing here with the remaining pins. The SAMD51N19A is a Cortex M4 processor. In the Cortex M family, you typically start with Cortex M0, M1, M3, M4 and then M7. The capability, speed and cost increase with a higher number of processors. I chose this processor because it has more pins and more speed and memory. I know the Arduino Uno is fully capable of driving motors, but I will be using artificial intelligence to program Caramel in future videos, so we'll need the full power of this processor. So that completes all the pins. I will now draw a rectangle to give a shape to this component. I could have split this component into multiple parts, but I just find it easier to understand my components when they exactly match the datasheet pins. We'll just move this box to the back. We need to name our processor. Usually we use U as a designator for the ICs. Let's save this component. We will now go to our schematic. I'll just make the sheet really big so that all the diagrams can fit in one page. Again, if you want to print this, then you may want to set it to a printable page size. I don't plan to print this, but would prefer to make it easy to understand everything in one page. I will drag and drop this component I just created from the library to the sheet, just to see if everything is properly done. Place the designator and the name where you can easily see it. Now let's search for the DRV8825 driver on DigiKey. I'm going to do exactly the same thing I did for the SAMD51. We'll find it, copy the part number, do a supplier search in Altium, paste the part number and then add it to my library. I now have the component in my library, so we'll start adding the pins like before. Let's go to the DRV8825 datasheet and start placing pins. We'll speed up the video as the steps are the same. The DRV8825 is a smaller chip with 28 pins. We want to control as many features of the robot as we can, so we'll be connected many pins to the SAMD51. Our DRV8825 is now complete. Let's draw a box around it to give it some shape. I will name it U ? Again with the manufacturer part number. Let's save it and place it in our schematic sheet. Another remaining main component is the Wi-Fi module, the WinC1500. We will find it in DigiKey and import the module into Altium like before. The steps are the same, so speeding up the video. The WinC1500 is a nice Wi-Fi module which communicates over SPI to the SAMD51. SPI is Serial Peripheral Interface. There are other interfaces like UART and I2C. We will cover these in more detail in future videos. Sometimes processors have a ground pin at the bottom of the processor. The WinC1500 has a battle ground pin. We will need to create a new pin for this, so we remember to connect it to ground. This will be pin 29. We'll just rearrange the pins to look better. Draw a box. Name it and save it. This completes our WinC1500 component. Let's drag it into the schematic to see if everything is okay. As we start thinking about putting things together, we need to start thinking about where the electrons will start flowing from, and that is the power. We need to bring down the 24 volts voltage to 3.3 volts for the SAMD51 and the Wi-Fi module. The driver 8825 will directly work on 24 volts. For this we need a voltage regulator. I am looking for a regulator which can handle at least 30 volts as input and will output 3.3 volts. I need at least 150 milliamps to drive the SAM B51 and the Wi-Fi module. So let's see what we can find here. This TI voltage regulator seems to meet all our requirements, so let's select it. Repeating the process again, I will bring in the component into Altium. I will open the datasheet and find a reference circuit to follow. I need to match the footprint as some components are available in multiple footprints. Now let's start drawing our circuit. Using the typical circuit diagram in the datasheet, we will start connecting the components. These 1 microfarad and 2.2 microfarad capacitors are called filtering capacitors. A capacitor acts like a bucket for DC currents, but is an open gate for alternating currents at some frequencies. So we want all the noise in our power supply to go through these capacitors into the ground. This will keep our power clean. We will start by placing a power net and call it plus 24 volts. This is the power coming from our power supply. I then need to add these capacitors. The input capacitor must be rated at least 50 volts because the input voltage we are providing is 24 volts. The output is at 3.3 volts, so 10 volts to 25 volts should be sufficient. We also want the package size of the capacitor to be small, but not very small. I will go with 0603 size for most components. 0603 means it is 0.06 inches by 0.03 inches in size. That is very tiny, but thanks to PCB layout software and microscopes for soldering, it doesn't matter. We will use this one. Let's bring it into Altium. Making a capacitor symbol is easy. Just 2 plates facing each other. Capacitors usually have a designator of C. Let's add a power port to represent our 24 volts power supply. The wire is used in Altium to make connections between components. Let's drag the capacitor into the schematic and make the wire connections. We will add a ground to the ground connection and connect the capacitor to ground. I want to add another bulk capacitor to the circuit, just for extra smooth power supply. This 50 volts 100 microfarad capacitor will act as a smoothing capacitor for the 24 volt input. This capacitor is polarized. This means that it can only be connected positive to positive and negative to negative. It can't be used in reverse. The symbol is slightly different to show the plus side. On the output of the regulator, we need to add another 2.2 microfarad capacitor. I'll just copy paste the symbol from the previous capacitor we used. We complete the output side of the voltage regulator by adding this capacitor and connecting a power rail for 3.3 volts. The NC pin and the enable pin can be left unconnected as per the datasheet. To be able to connect our power supply to this board, we need to provide a power connector like this one. I'll quickly draw this connector. Let's wire up the connector to the schematic. This completes the schematic of our power supply section. Now since we have our power ready, let's bring it to our microcontroller. The power supply section of the SAMD51 explains some important points about how power is connected to the microcontroller. We will start with the VDD-IO-B pin. This pin is here in the microcontroller. There are actually two VDD-IO-B pins. We need to provide filtering for each of these pins. Let's start bringing in these capacitors and start wiring the circuit as shown. For this inductor, the datasheet advises to use a ferrite bead. Which has an impedance or resistance of 220 ohms at 100 MHz. Ferrite beads are the opposite of capacitors. They will block noise and only allow the DC current to pass through. We will bring in this ferrite bead, draw the inductor symbol and connect it to our circuit. I will now go around the SAMD51 connecting all the different power pins and ground pins with the correct capacitors as explained in the datasheet. Microcontrollers have different internal subsystems which need to be powered up separately. This is why you see so many power and ground pins in a processor. This completes the power connections to our SAMD51. At this stage, if you switched it on, the microcontroller will start working but won't do anything yet. The brain of our circuit is now functioning, but without a heart and a heartbeat, it can't do much. The heartbeat of a circuit is provided by a crystal. Crystals provide accurate pulses to the circuit to make everything work. The SAMD51 allows us to add up to 3 hearts or crystals to provide slow and fast heartbeats to the circuit. We will be adding 2 crystals, one 32.768 kHz and another 25 MHz crystal. This should be sufficient for our robot's heartbeat. Just like a human heart, crystals are very sensitive to noise. We need to make sure we provide the correct load capacitance and position them carefully on the PCB. If we search for the X in 32 pin in the datasheet, we can find more details about which pin are allowed to be connected to these crystals. Let's find these crystals on DigiKey and import them into Altium. We can then draw the symbol of a crystal and draw the circuit diagram. We need to find the correct load capacitors for each crystal as provided in the datasheet. Sometimes the exact components are not available on DigiKey, so you may need to find close alternatives. It is very important to choose components which are ready to order. Otherwise, you won't be able to quickly prototype your PCB. This completes our crystal circuits. Now our PCB has a brain as well as a heart. If you switch it on, it is now pumping the heart and is ready to start doing some real work for us. The easiest way for us to understand which pins to choose on the SAMD51 for which function is to use Admiral Studio. Admiral Studio is a free software provided by Admiral/Microchip. It is similar to Arduino IDE but has several other features. One such feature called Admiral Start is very helpful in PCB design. I will create a new Admiral Start project in Admiral Studio. We will be needing this project in the future for programming also. We can search for the processor we want to use. Let's start by adding a Wi-Fi driver. We will need 13 PWM signals. We want 6 PWMs to control the 6 motors, 6 PWMs to control the power to the motors, and 1 PWM to add a buzzer to our PCB. PWM means pulse width modulation. It is basically a way to send square wave pulses to our motor controller or buzzer. We also want to add a timer to our software for basic timekeeping. Let's select the processor and create a new project. This adds all of our software components and assigns them default pins. The PWM functions are not available on all the pins, so we need to know which timer is being used for which PWM. Admiral Studio will show this to us quickly. Here we can see that Altium has made assumptions about where the Wi-Fi should be connected, where the MOSI and MISO pins of the SPI communication should be connected. We will quickly rename all the pins so we can easily understand which pins we are reserving for which function. We want to control the power to our motors using PWM pins. If you remember from an earlier video, this was being done by setting the tuning pot manually. I don't like the idea that I can't change the power to each motor as needed. Our robot may need overclocking of the motors if it is picking up something, and almost no power if it is keeping something down. We can see that the Wi-Fi chip enable and chip select pins are assuming PA00 and PA01, but we have connected these pins to our 32.768 kHz crystal. We need to change these pins and then update the circuit diagram accordingly. Another way to make wire connections in circuit diagrams is to use net labels. If I use the same label on two different pins, Altium will assume that they need to be connected. This keeps the diagrams free of wires and easy to read. PWM signals depend on timers in a microcontroller. These timers can generate different square waves on different pins. The DRV8825 expects only a square wave to move one step of the motor. This makes our task very easy. We could have also designed this circuit without using the 8825, but we would need to do all the work of managing the exact waveforms of the motors. We need just one pin per timer for the square wave. We can then match the pin in our circuit diagram. We will do the same for the remaining 12 PWM signals. This completes all our PWM connections to the microcontroller. Now let's complete the SAM-D51 Wi-Fi pin mapping to match the Admiral start project. Master in, slave out, or MISO, is a pin that the SAM will listen on. The MOSI pin, master out, slave in, is where the SAM will talk to the Wi-Fi on. The SCK pin is a clock pin to synchronize communication between the microcontroller and the Wi-Fi module. The IRQ pin allows the Wi-Fi module to interrupt the microcontroller to ask it to read the data available on the Wi-Fi. This completes our Wi-Fi connection pins on the SAM. Now let's complete the connections on the Wi-Fi module. The GPIOs are not used and neither are the I2C ports. So we will just mark these as not connected. The reset pin needs a 1 mega ohm pull down resistor. Pull up and pull down resistors are used to connect a pin to power or ground so that the pin is not floating. We will need to create this resistor. The SPI config pin also needs 1 mega ohm pull-up resistor. The wake pin is used to wake up the Wi-Fi module from the microcontroller. The interrupt line is connected to IRQN. We need to connect the UART TXT and UART RXT pins to a connector. This will be used to upgrade the Wi-Fi firmware later. Next, I will copy paste the net names for the MISO, MOSI clock pins. These names have to exactly match for there to be a connection. It is best to copy paste them. We won't be connecting the Wi-Fi module to battery backup as our main processor doesn't have a battery backup. So VBAT is connected to 3v3. We need another pull down for the chip enable pin, and then we add the ground to the parallel ground. This completes all connections of our Wi-Fi module. Next we go to our motor controller DRV8825. We will use this typical application schematic from the datasheet. We have 6 motors, so we need 6 drivers. I will set this one up for the first motor. Let's add the net labels. The V3P3 out pin creates a reference 3.3 volt output. We could have used this for our SAM and Wi-Fi module, but I'm not sure about the quality of this power, so I want to use a dedicated voltage regulator instead. The N-home and the N-fault pins both need 10K pull-up resistors. The CP pins need a 0.01 microfarad 50 volt capacitor. We will connect the 2 motor coil windings using 2 connectors. To control the power to the coil, I need to set a voltage to the AV-ref and DV-ref pins. We will use the PWM signals converted to an analog voltage by using a simple RC circuit. I have chosen 100 microfarad and 100 ohms as values by experimenting with what works. This is an easy way to create a digital to analog converter. Most microcontrollers have many analog to digital converters, but few digital to analog converters. We will copy our PWM power net name to this pin and also copy our control PWM signal to the step pin. Now the SAM D51N19A has 100 pins, but we are still going to be a little short to connect 6 motor drivers, so I have to compromise 2 pins. I have chosen to compromise the N-home pin and the N-fault pin. The N-home tells us whenever the 8825 goes to the beginning of the step cycle, and the N-fault pin tells us if there is an overcurrent or over temperature fault. I wish I could also get these 2 pins, but I can't. So we will just leave the N-home pin, but we can connect an LED to the N-fault pin. When this pin goes low, the LED will light up to show us that there is a fault in the driver. These are anyway rare conditions. An LED can be connected through a current limiting resistor directly to the pin of the 8825. This completes our 8825 circuit. Now we need 6 copies of this circuit, so I'm just going to copy and paste this 6 times. Then we will just rename all the pins slightly so they are different connections for the SAMD51. Our motor controllers are now fully connected to the SAMD51. We want to add a small buzzer to our PCB so our robot can make some cool beeping sounds like R2-D2. We will use this TDK buzzer. This reference schematic should work well. We also want to add two LEDs of different colors to our SAMD51, so we may use them to communicate different conditions to us when the robot is operating. To program our PCB, we will need to use an Admiral ICE programmer. The connections for this is explained in the datasheet. We need to create the 6-pin connector to connect to the Admiral ICE program. That completes our entire schematic. Let's quickly compile the schematic to see if we have any errors. Looks like we have a few unconnected pins. We'll fix this and recompile. All errors are now gone. Now when I add a new bill of material to the project, Altium finds all the components online and gives me a price estimate for the BOM. I can now order all the components quickly. Since delivery will take a few days, it is always good to order the components after completing a schematic, but before starting the layout. This step is easy because of the effort we put in earlier to draw our own components.
Guys, that brings us to the end of our 4th episode of Fun with Electronics. I'm getting really excited about Caramel now. In my next video, we're going to start laying out the PCB. So if you guys are excited about what's going to happen, subscribe, hit the notification bell for further videos I'll be posting. Hit Ratio out.